Hello everyone, hope you're doing great. Today I want to make a short video and explain about energy balance on non-reactive systems and processes. Hopefully you can find it useful for your study. You can refer to the previous PowerPoint that I uploaded on Moodle and follow up with this one. But you can I already solved some problems here. I hope that you can understand it better. However, when you are studying, when I am talking about some of the tables as your reference, I try to bring the tables here for your reference, but I recommend you check your books and even the module, because I uploaded the soft copy of the tables that you are using on Moodle. So you can refer to that table and find out the data that you may need during your solution and problem solving. You can see actually the review of the parts that we studied so far. We start with the types of the energy. We work on enthalpy. We talked about the open and closed system and energy balance on closed and open system. Last week we were discussing about how to use a steam table for evaluating steam properties. Today I want to discuss with you on energy balance on non-reactive processes, like heat exchanger, for example. So hopefully you find it useful. Just a review on energy balance on a single phase process when you don't have any phase changes. If you have an open system that there is no shaft work, there is no kinetic and potential energy, you can consider by neglecting the items that is not, that you can consider when there is no potential energy, when there is no kinetic energy, no potential energy, no work shaft, you can consider that changes of enthalpy is equal to heat actually transfer. So based on you can actually consider the changes of the enthalpy based on all the enthalpy of the inlet, of the outlet minus all the enthalpy of the component of the inlet. If it is a closed system, you already know that is the equation that we use. In the case you don't have kinetic energy, you don't have potential energy, and you don't have workflow or work shaft, heat transfer is equal to the changes of the internal energy. This actually we studied before. So we want to say that if you have a system that there is just one phase, mean there is no phase changes. For example, the component that you have is in the liquid, all actually through the system, or it is in the gas. There is no changes of the phases, not from solid to liquid, liquid to solid, solid to gas, liquid to gas. There is no phase changes. So in that case, you can say the internal energy is a function of temperature and a specific volume. So you can formulate it in this way. Delta U is equal to integration of the CV dt from T1 to T2, the changes of the temperature. This formula is when it is actually CV is the specific heat capacity at constant volume. You can just use this formula when there is no changes of the phases, right? I will let you know how you should do if you have phase changes. And actually the internal energy of a system that has more than one component is the sum of the internal energy of each component multiplied by its mass. I think this one is not new to you as well. The same way, if you have you want to formulate enthalpy of one component in one phase. In that case, H is a function of temperature and pressure, and you can formulate it based on this formula. That Cp in this formula is the specific heat capacity, it is heat capacity at constant pressure. So this equation is not valid when you have phase changes again. And the same thing actually happened here. Here is H, right? The enthalpy of a system containing more than one component is the sum of the enthalpy of each component. And actually we have this relation between the heat capacity as constant volume and heat capacity at constant pressure when you have ideal gas. That R is the ideal gas constant. So now we want to now go through some of the examples and show you how you can use these equations. So in the first example, they ask you to calculate the changes of enthalpy for a process in which 10 kilogram mole of air is cooled from 60 to 30 in the constant pressure process. So they already give you the CP, and they want you to calculate the changes of enthalpy. So we start with this actually first. So we know already the changes of the enthalpy is equal at constant pressure is equal to integration of Cp dt from T1 to T2. This actually, that is the specific enthalpy. As we discussed before, enthalpy rate or energy rate in form of enthalpy is equal to mass rate multiplied by a specific enthalpy or mole rate multiplied by a specific enthalpy. How you can choose between mass rate and mole rate, it depends on the unit of Cp, for example, because this one is given to you or you are taking it from the tables. So in our case, they give this actually amount of Cp, that is joule, kilogram, mole, actually Celsius. So because it is kilogram mole, you have to use this formula. You have to use mole. So enthalpy changes is equal to mole rate, or actually based on the here is actually the system is batch, so there is just mole, there is no dot, sorry for that. That is mole multiplied by the specific enthalpy. So what is the specific enthalpy that we already calculate? T1, T2, Cp dt. We already have Cp, I just substitute dt from T1, T2. And actually it's 10 kilogram per mole. The changes of temperature is from 60 to 30. That is the amount of the Cp, and that is dt. I am sure you know about these types of integration. When you have constant, you can bring out the constants, and that is just the integration that you can actually refer to the mathematics if you forget about that. So we calculate this one already. The second example, they ask you to calculate the heats required to raise the temperature of 200 kilogram of nitrous oxide from 20 to 150 degree in a constant volume vessel. The constant volume heat capacity, they already give you the heat capacity formula that which is in this formulation or equation. Again, it gave you the heat capacity in kilojoule per kilogram Celsius. So because you are having kilogram here, actually you can use M. So I started how we solve it, right? So we have constant volume. This is the amount of the mass you have. Starting temperature is T1, the final temperature is T2. There is no phase change. Why? I want you to consider that. And this is the amount of the Cv that is given to you by the equation. So we know delta U in the case, I give you the formula, is T1 to T2's integration of the Cv dt in this temperature range. I just substitute the amount of the Cv that is given to you by the problem, and I just wrote it. The temperature changes based on the problem is from 20 to 150 degree. That is the dt. So I am sure you already remembered. In that case, you can consider this one here, consider this one here. So I break the integration in two components of the equation. So this one, it will be delta T, and this one is the formula for integration. I just substitute the amount, and we finalize. And we know in that case, as I mentioned, heat transfer is equal to the changes of the internal energy. How you can convert the internal energy from a specific internal energy, you have to just multiply it by mass. So mass was 200 kg. Here we calculate delta U as 121. So we just multiply to each other, and it will be heat transfer inside the system. So that up to now, we didn't have any phase changes, right? But in the case if you have phase change during these changes of the state of the system, you have phase change rather than the changes of the temperature or changes of the pressure. You have phase changes, right? For example, you consider in that case, we have ice at -5 degrees and atmospheric pressure. We want to change it to vapor at 300 Celsius and 5 atmosphere. So to be able to, that one is not easy for us to calculate. As you know, we cannot get the absolute values of the enthalpy. What we have to do, we have to calculate the changes of the enthalpy. In this case, we cannot get this amount until we find out how it changed from this value to this value. Because we have some formula based on the phase change, we have idea how much is the, for example, enthalpy change based on the changes of the heat in constant pressure, constant temperature. We can quantify the values of the enthalpy changes. But in that case, we cannot quantify until we find the path, how it changed. How you can construct this path, it depends on you, right? However, we have to construct or hypothesize a pathway that you can quantify the values. For example, in case of the ice, we can actually quantify how ice from -5 can be converted to 0. Still, it is in the ice form because ice, melting point of water, we know, boiling point of water, we know. So we can consider in which situation it changed the phase. For example, from -1 up to 0, still it is ice, but you can change the temperature at constant pressure, right? From ice, to be able to actually reach to this stage, it can first melt, right? We have changes of the enthalpy for water when it is melted. So that is the phase change that you have. As it reached to water, as it changed from ice to water, you can increase the temperature at constant pressure from 1 to 100. What is this 100? It is the boiling point. So still here we have the changes of the temperature when the pressure is constant, and still the phase is similar. From here to here, we just change the phase from liquid to water at the same temperature and pressure. So now as you have the vapor and pressure is constant, you can increase the temperature to 300 degrees. And now, as long as you have the constant temperature to reach to that scale, you can increase the pressure at constant temperature to the final value. So delta H of this system is equal to changes of enthalpy in all through this path. That is way we quantify the amount of the changes of the enthalpy in a system by considering the subdivision of how it changed from this state to that stage. So in that case, in the first stage, we have actually temperature of the water at -5 up to the melting point of the water. We change this through the constant pressure, we change the temperature. So you can quantify the enthalpy changes through this formula, as we already discussed. After that, you have phase change from ice to liquid. So you have melting point. This actually amount you can find in table B1 at the end of your book. After it melted, it has actually, you have to increase the temperature at constant pressure up to the boiling point. So this is the way you can quantify. After that, you have another phase change, that is vaporization. And at the final stage, you can calculate the changes of the temperature at constant pressure to reach to the final value of the pressure. So that is the way we calculate we quantify the specific overall specific enthalpy for a pure substance through the sum of sensible heat and latent heat. Now it's better we go through one example. So we have a system that there is no reaction inside the system. We want to quantify how we can calculate the, we can actually conduct the energy balance in the system. You have actually ethylene benzene plant that in that, before this, actually in this plant, 200 mole per second of benzene is preheated from 25 to 100 degree at atmospheric pressure. This preheating happens in a heat exchanger that operates with 5 kg per second of the superheated steam at this temperature and pressure. So it is assuming that there is no pressure change or pressure drop across the heat exchanger, and there is no work has been done. No work of shaft, no work of the flow. So it asks you first to draw the flow diagram and actually see, show the data on it, and then determine the energy balance equation for the heat exchanger, and then determine the enthalpy and temperature in the heat exchanger outlet, and analyze the phase of benzene as well as the steam in the heat exchanger outlet with respect to their constituents and amounts. So first we go and draw the process. Here we have the whole actually diagram. We have a heat exchanger. Benzene enter this heat exchanger at actually in the amount of 200 mole per second. It is mole rate. The temperature, inlet temperature is 25, and it is atmospheric condition. It leaves this heat exchanger when it is heated up to 100 degree. It mentioned already the pressure is atmospheric and constant. How it will be heated? Through a superheated steam, using superheated steam. This steam, inlet steam, is superheated as it mentioned by the problem. That is the mass rate of the superheated steam, that is the temperature, and this is the pressure, right? So we know this one works at constant, actually the pressure of the steam and benzene are constant. It doesn't change through this heat exchanger, so it leaves the heat exchanger at 5 bars. But we don't know what is the status and what is the phase of the exiting water, right? If it is in superheated, if it is steam, or it is water, we don't know about that. The same way we don't know about the benzene. We know just the temperature is 100 degree and pressure is atmospheric. The first step that we know that we can assume in this situation whatsoever energy transfer, whatsoever energy lost by the steam have been captured by the benzene, right? So that is the first assumption that we have. So to know how benzene changed from this stage to this stage, if it was water, like for example for superheated steam, you have idea how much is the H. Actually, for some of the condition, you already have tabulated data in B5, B6, B7, right? So for H, you can quantify by using the tabulated data in B5, B6, B7. But for benzene, we don't have this tabulated data. We have to go through calculation. To be able to calculate the changes of the benzene from this stage to that stage, we have to know how benzene change, right? So for this actually data, you have to go to table B1. In table B1 of your book, it already mentioned about the physical property of different compound, right? For example, in our case, benzene, it showed the benzene, the compound, the formula, molecular weight of the molecular weight, right? So what information you have to capture from here? It showed the melting point of that component. So for example, if it is before, it is less than this amount, means it is ice, it is solid, right? From this value up to boiling point, this is boiling point. You know, this compound is in liquid form, right? So below this is solid, between this is liquid, after this is vapor. True? So that is the energy changes of the enthalpy for melting or for fusion. So you need this, if, for example, it changed from the solid to liquid, this amount of the energy will be produced, right? So after it, and this actually changes of the enthalpy at boiling temperature means the amount of the energy that will be converted, that will be actually produced if it will be changed from liquid to vapor. So it is changes of the energy in terms of phase changes, actually, if there is phase changes. So this value, if for example there is phase change, you can refer to this value, right? And this melting point and boiling point are helping you to guess how much, so how was the phase changes inside the system, right? And these two component, later we will talk with them about the heat of formation and heat of combustion, right? So we will go back later when I discuss with you about these two types of heat. We will refer to these values later. So here, as we know, benzene entered the heat exchanger at 25 degrees. We know it's already above the melting point, so it is and it is below the boiling point. So first of all, up to boiling point, it is still in the liquid phase. As it reaches, so it is liquid. After it reached to boiling point, there is one phase changes from the liquid to gas. And finally, to reach the final value, we need the vaporization, actually. That one is just increasing the temperature at constant pressure. So to calculate the changes of the enthalpy from 25 to 100, you have to calculate all these changes. So delta H is a combination or sum of all these changes of the enthalpy. So for this one, we have to calculate based on the formula that I already introduced to you from 25 to 80. Then you have phase changes that you can find it out because it is evaporation. You can get this, this is a value for vaporization. And finally, it is the temperature change at constant pressure that you have to find it from this formula. So here we have liquid, in this phase we have evaporation, and finally we have the gas form. So now I have to find out how to quantify this value and how to quantify this value, because this one we already got it from the table, right? How you can find CP? Sometimes maybe the question, the problem will give you the CP, but if they didn't give you, you have to go to table B2. In table B2, you are given the formula of CP. There is form 1, form 2. It here in the table, it actually states for you which form you have to use. For example, for benzene, you have to use this form 1 of the equation. So it already gives you if it is liquid, if it is gas. For us, we need both liquid and gas, because in the first stage, it is in liquid form. In the last stage, it is in gas form. So you have to just write the formula of CP. How you write the formula of CP? Based on this, because it is form 1. A plus BT plus CT2 plus DT3. So for us in liquid form, we have A, we just substitute here. We have B, we just substitute here, right? We don't have C or D. So I just write this one, the value 126.5 multiplied by 10 minus 3, because it is the correction factor of the table. I just put plus this one. I just substitute. And at the last stage, we are in the gases, actually gas phase. So we have to use this, right? This is A, this is B, this is C, this is D. I just substitute this one in this formula that is given by the table. So you have access to this table at exam, so don't worry. Just read the data and put it in the formula as I did. So the rest is just some integration. I am sure you already have the integration if it is just constant value, or if you have actually how you have to deal with that one. If you have any problem, let me know. I will guide you more. But this is the integration rule that you have to use. So after we calculate all these values, we just put it in the final stage and add them together. Because we need to calculate the energy, we have to multiply we have to need the energy in terms of rate. We have to multiply mole rate by a specific enthalpy. So I just multiply this 200 mole per second multiply by kilojoule per mole of a specific enthalpy. So that is kilojoule per second. That is the amount of the heat Benson gain, right? Benson gains from steam. So now, as I mentioned, this amount of the energy that Benson gains, steam lose, right? So you can say this one you already quantify. That is the amount of the that is the values you get from the table, right? So you know, in the beginning, you don't know what phase you have, so you have no idea what is the enthalpy. At the initial stage, you know, it is superheated steam at a specific temperature and pressure. So you can, for superheated steam, you have to go to table B7, right? And find out the specific enthalpy at that temperature and pressure. So I just read this value from the table at 5 bars and 350 degree. So we just substitute whatsoever we have. H2 we don't have. We just calculate from this equation. Now we want to guess how much, actually, what is the stage, what is the state or phase of the exit steam. So I already found in the table, if you go to table B6 at 5 bar, because it is the exit liquid or material from the heat exchanger is in 5 bars. You can read the specific enthalpy of water and steam. This amount that we find is between these two. So it is a wet steam. It is a combination of water and steam. So you can say H2 is the combination of some part is a steam. So you can use HV, XV, the composition of the steam, multiply by the specific enthalpy of the steam, plus the rest is liquid. So we know it is H2. That is the amount of the enthalpy of the steam multiplied by the composition. And this is the amount of the specific enthalpy of the liquid multiplied by its composition. Through this equation, you can calculate what is the composition of the steam. As you calculate the composition of the steam, you can calculate the composition of the liquid. So you can say the superheated steam that enters the heat exchanger leave the heat exchanger in forms of wet steam as a composition of the 43% of vapor and 56% of the liquid. Actually, I typed some of the solution here. I hope that you find it useful. Now, if you don't have any problem, if you have any problem, please contact me. We will find a way you understand it better. But I want to ask you to go through this assignment and test yourself if you understand what we studied today. Have a nice day. Take care. Stay safe. Bye.